Welcome back to our video series on integration and differential equations. In this video, we're going to do a couple more examples of the power form. Here's our first example. We would like to evaluate the following integral. In the denominator, we've got 3x plus 4 times the 8th power of ln, and we want to get this whole expression integrated with respect to x. So the general tip when working with the power form, in order to get this integral rewritten in a nice way, typically what you want to substitute is u equal the quantity that's being raised to the power. So if we look at that 8th power sitting in the denominator, the quantity that's being raised to the power is ln 3x plus 4. So let's use that as our u. Now if we refer back to our previous video, we all know our derivatives well, hopefully by this point. The differential du is going to look like the following. We'll take the derivative of this ln function, so 3x plus 4 goes into the denominator. Derivative of that function is 3, that goes on top, and to make that a differential, we'd multiply by dx. Alright, so at this point we look back up at our integral. We can say, yep, we've accounted for this 8th power of ln. We'll be able to write that as u to the 8th. But what about the rest of the integral? We've got this dx over 3x plus 4. So that's what we want to solve for here. I'll copy that down. So this is the expression that we're looking for, and we want to ask ourselves, well, how do we get from this line here, how do we get from du to a transformation of du? Well, what we'd have to do is divide by 3. So we could say du over 3 is the same thing as dx over 3x plus 4. So that is our substitution done. I'm going to put that in a box, and we can start to rewrite our integral. So continuing our work over here, I'm going to say the integral in the question is equal to the following. Well, we know that the dx over 3x plus 4 can be written as 1/3 du. So I'll do that. And then what else we've got in the integral? We've got the 8th power of ln in the denominator. And remember, we've written ln as u. So really that's u to the 8th in the denominator. All right, so this almost looks like the power form now. One thing we could do to make that a little easier to work with is just write that u to the 8th in the denominator. Let's rewrite that as u to the negative 8. So there we go. We've got 1/3 integral of u to the negative 8 integrating with respect to u. So now doing our integration, we're going to increase the power here. It's going to become less negative, so it's now u to the negative 7, and we need to divide our coefficient by negative 7. So it's going to be minus 1 over 21 at this point. And since this is an indefinite integral, we need a plus c in our final answer. Okay, so to get that final answer, we need to put everything back in terms of our original variable. So remember that this u is really ln of 3x plus 4. So that entire ln is getting raised to the power of negative 7. So that is one way to give our final answer. Alternatively, we could move the 7th power of ln down into the denominator. We could say it's 21 times ln of 3x plus 4, all raised to now the positive 7th power, and we'd still have plus c on there. So two good ways of giving your final answer. So let's try a definite integral now. We're going to integrate the following expression from 0 to pi over 28. Well, we're hoping to get something that looks like the power form, and in looking at this integral, I'm really seeing two parts to the integrand here. I'm seeing a 4th root, and I'm seeing a secant squared. So we've said that in general you want to let u equal the quantity that's being raised to a power. In this case, u would equal 1 plus tan 7x. This 4th root here really acting like the power 1/4. Okay, so that would be a great choice because when we go ahead and we calculate du, we're going to get something that involves this secant squared expression. So let's see specifically what we're getting. Taking the differential, well, if we take the derivative first, derivative of 1 is 0. Derivative of the tan is going to be 7 secant squared 7x, and to make that a differential, I'm going to multiply by dx. Okay, so it looks like we're on the right track here. What we've got in our integral is secant squared 7x times dx. So let's in fact lump all of this together. Say that's our expression here in the integral that we're looking for. To get from this step to this step, what are we doing? Well, we're dividing by 7. So on the left side we'd have du over 7. Okay, so that looks great. Now we'll deal with the limits of integration in our next step. But before we do that, I just wanted to point out, sometimes when you're approaching an integral like this, you might have a little bit of debate about what u should equal, and that's fine. So if you had approached this and you had said, well, I'm seeing that secant is being raised to a power, maybe I could let u equal secant of 7x. Okay, fine to try that. Let's see how well that works. If we take the derivative of secant 7x, we're going to get something involving secant and tan, and then we'd have to ask ourselves, does that look like the other part of the expression? Does that look like the fourth root of 1 plus tan 7x? And we'd say, no. So after a little bit of thought, we could rule that out as a possibility. And ultimately we'd come back to the idea, hopefully, that u equals 1 plus tan 7x. So if there is a little bit of trial and error there, that's fine. With a bit of practice, you start to be able to choose the correct u on your first try. Okay, so there we go. We've got this mostly set up now. Let's think about how the limits are going to change. So when x equals 0, u would equal 1 plus tan of 0, and tan of 0 is 0, so that's coming out numerically to the number 1. And let's see what happens when x equals pi over 28. So u would equal 1 plus tan of, inside the tan we've got 7 times x, so that's going to be pi over 4. And tan of pi over 4 is equal to 1, so overall u is equal to 2. Alright, so it looks like we're on the right track here, and let's go ahead and try to rewrite this integral. So I'm going to continue the work over here. I'm going to say the original integral here is equal to now the following integral. Our limits are changing. They're now going from 1 to 2. And if we start to rewrite our integral here, the fourth root we've decided could be written as the fourth root of u. So that's great. And then we can grab this secant squared 7x dx, and we've said down here that's equal to du over 7. So let's put the 1/7 out in front there. And there we go, we've got a nice example of the power form. So in order to do our integration, might find it a little bit easier to rewrite that fourth root as u to the power 1/4. And we'll keep our limits of integration on here. We're integrating from 1 to 2. So now we can go ahead with our integration. Okay, we'll keep this coefficient 1/7 out in front. When we integrate u to the 1/4, we get u to the 5/4, and that'll be times 4/5. So I'm just going to put a dot here for the multiplication. And this is a definite integral, so we will be evaluating at u equal 2 and then at u equal 1. Alright, so let's clean this up a little bit. Our coefficient in front is 4 over 35, and I'll put some brackets here. We're going to be multiplying that by the different powers of u. Subbing in u equal 2, we'd have 2 to the 5/4, and then subtracting off the value at 1, plugging in 1 here, we'd have 1. 1 to the 5/4 is 1. Okay, so this is an exact answer if that's what's required. If you wanted a decimal approximation, we could say that's approximately 0.16 if we plug that into our calculator. So there we go. We've had a little bit more practice with the power form, and we've done both an indefinite and a definite integral. So we'll see you in the next video.